There are two different ways in which random variables can be equal to one another. And to show you what I mean, let's use an example. Suppose we draw two people at random with replacement from some population, and let's say x is the age of the first person and y is the age of the second person. Both x and y are random variables here. But is x equal to y? The answer to that is no, not necessarily, because the age of the first person we draw could be different of the age of the second person we draw. It's possible that they're the same, but in general, x is not equal to y because it doesn't always have the same value as y. But x and y in this case have the same distribution because both of their distribution is the same as the distribution of ages in our population. So here, x is not equal to y, but x and y have the same distribution. And so now hopefully it's a little more clear when I say what I mean when I say that there are two different ways in which random variables can be equal. The first, more stronger statement is that x and y are equal, period, if for every possible sample s, the value that x assigns to s is equal to the value that y assigns to s. And so this is bringing back our notation that represents a random variable as a function of a sample. So what this is saying is that x and y are equal if the output of x for every sample s is the same as the output of y for every sample s. And now if this is true, we say x and y are equal. A less strong condition of equality is identical distribution. And so we say x and y are identically distributed if the distribution of x is the same as the distribution of y. And if this is true, we can say x and y are equal in distribution. Let me give you another example. Let's suppose x and y are the number of pips we see on two rolls of a dice. So x is the number of pips we see on the first roll, and y is the number of pips we see on the second roll. X and y are not necessarily equal, right? Because the number of pips we see on the first roll could be different than the number of pips we see in the second roll. But both x and y have the same distribution. They both take on the value 1 with probability 1/6. They both take on the value 2 with probability 1/6, and so on and so forth. So in that dice example, and in the example we talked about in the last slide, we would say x and y are equal in distribution, but not equal. And so down here, we have the fact that this first statement is stronger than the second statement. So if x and y are equal, then it is also true that they are identically distributed. But just because x and y are identically distributed does not make them equal. So this first statement implies the second statement, but the second statement does not imply the first statement. In both of the examples that we looked at, the one of taking people's ages from a population and the one of rolls of a dice, were examples where x and y were identically distributed, but not equal. And so that was a lot of technical jargon that we just went through. The only way to really confirm your understanding of the topics that we just talked about in this video and in all of these videos in general is by doing the quick check questions that we've created for you to do in between these lecture videos. These are linked on the website and they are on Google Forms, and they'll tell you right away if you got the questions right or not. And it's really important that you do these because learning happens when you make an active effort to remember things and not just a passive effort of watching me or some other person talk to you through a video. So you really need to be doing these quick check questions, and especially for this video, you do.